Good morning, everyone, and welcome to today's class. Today we are looking at the analysis of variance, which in brief is called ANOVA. Just like we have done in the other topics, we shall be looking at the parametric technique of conducting ANOVA, as well as the non-parametric technique of conducting ANOVA. And the focus in this class will be what we call one-way analysis of variance. And later on, we'll be talking about two-way analysis of variance. The non-parametric techniques that will be used here, we have what we call the Kruskal-Wallis and the Friedman test. So those two tests comprise of the non-parametric techniques that we'll be talking about here. So the objective of today's class is the comparison among more than two groups parametrically. So if you want to compare the means of more than two groups parametrically, then you can use the analysis of variance. Then we shall also be doing the same comparison of the mean of more than two groups non-parametrically. And then later on, we shall be talking about the two-way analysis of variance. Okay. So to start us off, we are going to look at one-way ANOVA. One-way analysis of variance. So we start by defining the notations. So we can say let xij denote observation number j So we're saying that you let xij denote the observation number j in group I. For example, x47 is the 7th observation in group 4. Okay, then x bar j, or x bar I, let that denote the mean for group I, because we mentioned that we have more than two groups. So we expect I to be at least 1, 2, and 3. Yeah? Then we have x bar dot to be the overall mean for all the observations, irrespective of the group, if you are to compute the mean of all the observations. Let me have a sketch to illustrate basically the kind of data we are talking about in this scenario. So we are talking about some data which looks like this. So these are my individuals or my observations all the way to n. Usually I prefer to call it capital N. Then let's say my variable of interest is age. So we have age in this column. Then also have some variable or some for grouping mechanism here. So, and I have three groups. So I have individuals who are in group 1, I have individuals who are in group 2, individuals who are in group 3. Usually what we are doing using the t-test, we were stopping here. With the t-test, we were looking at two groups or even one group like that. So we were looking at this. So if you just have that, you can use the t-test. So difference of means. Mean between the groups. But when you have a third group, like the one we have here, now you can no longer use the t-test. So you use another technique. And the technique that you use when you have more than two groups is now what you're calling the analysis of variance technique. Okay. So let's continue. We start by saying that the observation can be decomposed as follows. The observation xij can be decomposed as follows. Okay, so you can say that xij is equal to the overall mean plus you have x bar of I minus x bar dot. So you have that. Then you also have plus xij minus x bar of I. All these things are easy to see, like especially the second term and the last term. What are they all about? I'll be illustrating that in a short while. So suppose I rewrite this data in this format. I write my data in this format. So I'm getting this information from here. So I have information for group 1. So that is information up to this point, from the top up to this point. Then I have this one as the second set of information. It's my group 2 here. I record the edges. Then this is my last set of information, group 3 here. Then for each column now, I'm able to get the mean. So those are my x bar i's. So in this case, I runs from 1, 2, 3, like that. Then I'm also able to get the overall mean or the grand mean. And the grand mean is actually the combined mean. And we know this is a formula for combined mean. So once I get x bar 1, x bar 2, x bar 3, I don't need to sum up the values of edges everywhere, divide by the overall number of observations. So I just take n1 x bar 1 plus n2 x bar 2 plus n3 x bar 3 divide by the sum of the sample sizes, which will give me a capital N. So basically that is it. So when you look at this expression here, this item here, the second one here, we are taking each value of x bar, you take away this guy. So we have something like this, x bar 1 minus x bar dot. So that's one thing. We also have x bar 2 minus x bar dot. And then we also have x bar 3 minus, these are dot, not 2. These are dot, like that. And then we also have this. That's the second item. That's how it looks like. Then when you look at the last one, we are taking each observation, xij, you take away the mean of that particular group. We take away the mean of that particular group. So basically, what is happening in the last item is that we are taking, for example, x1 here minus x bar 1 minus x bar 1 minus x bar 1 minus x bar 1 all the way to the end. When you come here, you take minus x bar 2 minus x bar 2 minus x bar 2 all the way to the end. And again here, minus x bar 3 all the way up to the end. So basically, that's what is happening in this equation. So let me have some description down here. So that explanation is what you've written down there. And we can say that this particular equation here, you can call this one equation number 1, is informally corresponds to equation number 2, where you have xij is equal to mu plus alpha i's plus EIJs, where EIJs, of course, are the errors or the residues or the noise. And we're assuming that the noise has a mean 0 and constant variance. Okay. Then we say that in which, so equation 2, in which the hypothesis that all the group means, are the same, where that hypothesis implies that all alpha i's are 0. It implies that all the alpha i's are 0. So when the group means are the same, I want to take you back here if this mean, and now I hope you can see the concept of hypothesis testing for more than two means, or for the mean of more than two groups. If these three values are the same, what does it mean about x bar dot? This guy here. It is also equal to this. If these three are equal, it means that they are all also equal to that. Then what does it mean when you come here? It means that this will be 0. And that's what is corresponding to this. That's what we are calling the alpha i's. So if all the group means are equal, then it means that the alpha i's are all equal to 0, where the alpha i's correspond to these differences here. So this is alpha 1, alpha 2, this is alpha 3. Because we're saying this is the same as that, it's the same as that. And if those three are equal, then the overall mean is also equal to them, like that. Okay, so basically, that's the logic. So that implies that all the alpha i's are 0. Okay, then it's good to note this about the errors. The error terms, the epsilon ij's are assumed to be independent and have the same variance. Okay, so it sounds like we are doing a regression model. That feeling is okay, because it looks like this is a type of regression model, this one. All right, then let's continue by looking at something else, the sum of squared deviations. Let's have a subheading here. The sum of squared deviations, or variation. No? Of the in this equation number 1, the parts that have under brackets of the under braced terms. I mean these parts, so this part and that part, are the under braced terms, or the part with the under brackets. So there are two types of deviations that we're going to mention here. There's a third one which will come in. So one of them is called the variation within groups. Variation within groups. Okay, and I hope you can notice when you come here, this is what we are calling variation within groups. Within a group, what's the kind of variation there? Okay, so we say that this is given by, we denote it by SSW, sum of squares within groups. So this is a variation for the sum of squares within groups. So this is given by, I'm going to have double summation like that, where I'll sum over the i's, I'll also sum over the j's. Then I'm summing what? The individual observations minus the group mean, like that. Then I square. If you come back here, I'm taking the observations minus the group mean, but now I need to square them. So once I square, I need to sum those squared deviations. That's what we are calling the variation within groups, or sum of squares within groups. Sum of squares within groups. Whatever we have done there is exactly what we do when you want to find the variance of a particular group, because you'll take the difference, you'll take the deviation from the mean of that group, you square, then later on we expect to divide by the degrees of freedom. Okay, but here we're focusing on the sum of the squares. That's the numerator in the formula of variance. Okay, so that's one of the square deviations. Then we also have variation between groups. Variation between groups. and we call it SS between. So this is given by summation, double summation over the i's and over the j's. And we have x bar I. So that's the group mean. You take away the overall mean, then you square. So basically, using this illustration of ours here, you are taking a value like this, you take away this, then you square. Then this is, and of course now you are summing up. Now you are summing them. So you take this, this value minus this, you square, plus you take this value minus this, you square, then you sum, then you add this, x bar 3 minus x bar dot squared. So you sum those deviations from the deviation of group means from the overall mean. Okay, and if you recall something that we did in regression analysis, actually not necessarily in regression analysis, when we are testing a hypothesis for the mean, there's something called the standard error of the mean, standard error of x bar. And how do we denote that? You can denote it like this: sigma, sigma of x bar, which is the same as sigma squared divided by n. Then you take square root. Then you take square root, which is sigma over root n. So that means if I want the variance, sigma squared x bar is equal to that. So basically, this is the kind of thing that we are doing, because we are finding the variance. When you see, when you take these values, when you take this value minus that, you square, plus this other guy minus this, you square, plus the last one, you square. We are attempting to find, it is the same procedure we would use to find the variance of these three values, if there were just three like that. If you want to find the variance of this, you take each observation minus the overall mean, you square that deviation, then you sum, divide by the degrees of freedom. In this case, we have 3 observations, so we'll be dividing by 3 minus 1. So here, we are finding the mean of the variance of the group means. We are finding the variance of the group means. And that is equivalent to what we are calling if you take the square root, then you end up with the standard error of x bar, which you know the formula is given by this. And so the variance of x bar is also equal to sigma squared over n. And you agree with me that you can also rewrite this as n sigma squared x bar is equal to that. You can write it like this. You can write it like that. So from that kind of argument, we can also rewrite this as equal to summation over the i's of ni. Then you have x bar I minus x bar dot with a square. You can also write it in that format. You can write it in that format using the same analogy we have here. Okay, then it can be shown, and we're not going to show that. It can be shown. It can be shown that if you take SS between plus SS within, you will get SS total. So this is total. Let me not write in full. SS total, which is given by summation, double summation of I, j. Then we have xij minus x bar dot squared. So it can be shown that if you take these two, let me call this one number 3. Let me call this one number 4. And then this is your number 5. This is your number 5. Huh? It can be shown that 3 plus 4 is equal to number 5. Then, as you can see, the kind of items we have in equation number 3 and 4, they are just the numerator when you are trying to find the variance of something. They are the numerator of some variances, the formula for some variances. So we want to actually get the actual variances. So, and we shall be just calling it the mean, because we have just summed. We know that the variance is some mean. The variance is some mean because you sum up some items, of course, some square deviations, divide by n, or divide by the degrees of freedom to be more specific. So we can say that we can normalize. We can normalize the sum of squares by calculating the mean squares. And these mean squares are actually variances. Okay? As you know, if you, for example, if we're talking about a single variable like variance of x, we know this is given by summation of x minus x bar divided by n, or n minus 1. Okay. So basically, what we have here is the numerator, is some numerator like this one. What we have in equation number 3 and 4 is some numerator like this. Some numerator like this. So we want to divide by the corresponding degrees of freedom. We want to divide by the corresponding degrees of freedom. Then we see what we're going to get. So we end up with the mean sum of squares within. The mean sum of squares within. So we're working with the first one. We just want to divide this by the number of items that we are summing, or by the degrees of freedom corresponding to that. So this is sum of squares within divided by n minus k. Of course, n is the overall number of observations. In other words, it's the summation of the ni's, or the i's. If you sum all the sizes or the number of observations in every groups, so for example, here, so you see the number of observations in every group are not necessarily the same. So maybe in the first group, you have this number of observations. In the second one, you have this number of observations. In the last group, you have this number of observations. So you need to sum them to get n. That's what I'm calling n. If you have 3 groups, okay. If the groups are of equal size, then we just take n times 3 in this case. N times 3 will be equal to your capital N. Okay. Then we also have the mean sum of squares. So of course, here k is the number of groups. K is the number of groups. Okay. Then mean sum of squares between will be given by sum of squares between divided by k minus 1. Okay. So back to our illustration here. Here we have 3 groups. So we have this guy, and this guy. So in our case, k is equal to 3 here. So it means that when you want to find the mean here, you will be dividing by 3 minus 1. So we'll be dividing by 2. We'll be dividing by 2. If you look keenly, let's continue numbering them. Let's call this one number 6. Let's call this number 6 and this number 7. If you look keenly, you will notice that number 6 is the pooled variance. It is a pooled variance. The pooled variance that we are used to is a pooled variance obtained by combining the group variances. The group variances, and is therefore an estimate. You can say is an estimate of that. It's an estimate of sigma. It's an estimate of sigma. You can say even sigma squared. Then let's talk about the second expression number 7, or equation number 7. We say that if there is no true group effect, if there's no true group effect, in other words, we are saying if these mean values x bar 1, x bar 2, x bar 3 are the same, if there's no difference of mean between the groups or among the groups, okay, then that means that m, the mean sum of squares between, is also an estimate of sigma, just like the first one. It's also an estimate of sigma. An estimate of sigma. That tells you that the pooled variance, if you take the ratio of equation number 6 and equation number 7, or the vice versa, if you take the equation number 7 divided by equation number 6, then you end up with 1. You will get the number 1 because they'll be estimating the same thing. They are equal, or they are not different in a significant way. If there's no group effect, then the ratio of these variances is equal. The ratio of these variances is equal to 1. If there's no group effect, if you take equation number 7 divided by equation number 6, you will get a 1 because the two items will be estimating sigma. Okay. Otherwise, that is now if there is group effect. So we're saying otherwise, it gives the difference. It gives the difference between group means. It gives the difference between group means. That's what we are actually looking for. Our objective is to check where there's a difference between the group means. Let me say that to test the significance of the difference between the group means, we compare the two variances. Because equation number 6 and 7 are some variances, as we mentioned earlier. So we compare the two variances. And I think you remember when in hypothesis testing, we were doing some test of hypothesis to compare two variances. So here we compare the two variances, that is the mean sum of squares between and the mean sum of squares within, like that. So this explains why. This explains why the procedure is called the analysis of variance. It's called analysis of variance. We are calling it analysis of variance, but in the actual sense, we are checking, we are comparing group means and testing for their significance. Okay, so that's why it is called analysis of variance, in brackets ANOVA. ANOVA. Okay, even though we call the procedure analysis of variance, even though the objective is to compare group means. Compare group means. I hope that is clear. So basically, when you have more than two groups, clearly you cannot use the t-test that we were using in our first topic. So you switch to the analysis of variance, and you do this by comparing some two variances, the mean sum of squares between and the mean sum of squares within. So what is the test statistic that we use here? The test statistic as you know, when you have two variances, you only divide them. Okay, depending on your assumptions, you may end up with an F statistic like we saw in hypothesis testing. So you say that under the null hypothesis, under the null hypothesis of identical group means, the test statistic is given by you take MSSB divided by MSS within. You divide those mean sum of squares. The between one is the one that goes to the numerator. In regression analysis, that is equivalent to what we call the explained sum of squares, the mean of the explained sum of squares. And maybe you will notice that the ANOVA, analysis of variance, is also applicable in regression analysis. Actually, in a standard regression output, there is a table there called the ANOVA table, where the numerator here is given by the explained variation, the mean of the explained variation, divided by the mean of the unexplained variation, or the residual. So this item here has an F distribution with numerator degrees of freedom given by n, capital N minus k, and the denominator degrees of freedom given by k minus 1. And as you know, these are division of, we are dividing two variances. And clearly, all the values, the numerator and the divisor, are positive values. They can never be negative. Maybe, let's say they are non-negative. So that means even their quotient is also non-negative. That explains why this kind of test is a one-sided test, and more specifically is an upper tail test. This kind of test is an upper tail test because there's no possibility of having a lower tail test. Okay, so let's note that this is a one-sided test, or upper tail. More specifically, an upper tail test. Okay, so that's the briefly the theory that I wanted us to catch up with before we look at now implementation of this in using R. I don't know if there are any questions before we proceed. So now let's switch to R to see how we can implement analysis of variance using R. So we are considering some data in the ISWR library known as red.cell.follet. Okay. So I want to call that particular data. I also want to include another library. This is not for the sake of the analysis, but for the kind of output that I want to see, especially when I'm viewing tables. You notice that most of the tables that you get from the default R code, they are not quite pleasing. Like for example, if you want to transfer them to a document, they don't look so nice. So there's a library here that can help you in presenting your tables in a very nice format. And this is called NITAR, this one. Hope you can see it. Huh? This is a general purpose tool for dynamic report generation in R. Okay, it's an alternative tool to Swift with a more flexible design and new features like sketching and finer control of graphics. Okay, it is not limited to LaTeX, and it is ready to be customized to process other file formats. So NITAR, so I'll also be having that. And you'll see the difference when you use NITAR and also when you don't use NITAR. So I want to call the data, this data here, red.follet. So I want to call it, I want to give it a name like red. I want to give it a name, red underscore cell. I just want to call it like that. Huh? So this is red dot is one. So this is the data that I want to deal with. And I want to view it in the console. Usually I prefer not putting the viewing code here because it's not something that you want to run every time you are revisiting your code. So if I say red underscore cell, so how does the data look like? So this is the data. You can see it's in form of a data frame. So we have the variable of interest here, which is folate. And then we also have another variable here, which is also good, the ventilation. Okay, so we have folate. If you scroll, you will see that all these, so this is the grouping variable, the ventilation. As you can see, all these, the ventilation is the same. Okay, the ventilation is the same up to here, at some point here, up to here, ventilation is the same. Then after that, from individual number 9 going down, we have some change. The group is different. As you can see, this is comma OP. The other items remain the same, all the way up to item number 17. Then from item number 18, you have a new grouping. So in this data, folate is grouped into 3, according to the variable we are calling ventilation. So basically, we want to check the mean within the first type of ventilation, and the mean within the second type of ventilation, and the mean within the last type of ventilation. Are they equal? Are they differing significantly? Basically, that's what you want to do. Okay. So I want to look at, so this is how I use, let me do this. Let's do head of red underscore that. So this is how the output will look like. Okay, these are the first 6 observations. They happen to come from the same group, all of them. Okay, but when I say k-able is a function which is defined within this library here. I say k-able, then I open bracket there, and I put a closing bracket there. There is a typing error here. Like that, huh? When you run this, hope you see how it looks like. Looks like a nice, the table is nice, better than the first one. So this is something you can even copy and paste on your document. If you're doing a report, this is well presented than the first one. Okay, so you can transfer this to your Word document and so on and so forth. If you're working with the LaTeX, then or if you're working with R Markdown, then this will be presented in a very nice table. To be presented in a very nice table, as you can see there. So we have 2 variables, folate and ventilation. Okay. Then we may want to get started with the data, we may want to attach the data. Attach to the data. This is a red underscore cell. We want to attach the data. Then let's look at this, a summary of the variables. You see what kind of data are we dealing with, like that. Okay, so the first variable is folate, and these are the descriptives, the minimum value and the maximum value. The first quartile, the third quartile, the upper quartile. Then we have the median and the mean. Okay, then ventilation, we have this observation here. So ventilation has some level, so it's a factor. And the first level here has 8 observations. So there are 8 rows under this kind of label. There are 9 rows under this kind of label. And then there are 5 rows under this kind of label. If you revisit the view, if you view again, I think it's here. If you view again, you notice that the first level here has from the first individual all the way to individual number 8. That's why we are being told there are 8. Then the second one, which is it nitrogen oxide plus something? Then we're running from 9 all the way to all the way to number 17. So those are 9 observations. Then the last one are 5. The last one are 5. So if you count 1, 2, 3, 4, 5, that's all. So that's the summary. You may want to, it would be very good if you check the nature of the variable, which we are calling ventilation. It would be very nice if you check, because we want it to be in a certain format. So if we say structure, if I say structure of ventilation, I want to see the structure of that variable, and that variable is a factor. In other words, is a qualitative variable. It's not a quantitative variable. So the items found here are factors. So these are factor with 3 levels. A factor with 3 levels. The first level is called this. Okay, that's the first, the first 8. The second level is given by this. And the third level is ... the last one here. Okay, and the levels are labeled level 1, like these ones are 8 observations. And then the 2s, you expect them to be 9, but you see they cannot display all of them. So usually the grouping variable should be a factor all the time when you want to do analysis of variance. If you don't make this a factor and you try to find the ANOVA for this one and this one, then you'll be doing regression analysis. You'll be assuming that these are quantitative variable or is a numeric value. So you'll be performing regression analysis, because actually whatever we are calling here analysis of variance is very close to what we call the regression analysis. Actually in R, we use the same kind of object. So we use the model formula. We use the model formula in ANOVA, just like we did in linear regression. But now, instead of extracting the output using summary, the way we are doing in regression analysis, we extract the output using a certain function known as, you can call it ANOVA. You can extract the output using the function called ANOVA in R. All right, so back to our data, or back to our codes. So, so we're saying that the specification of a one-way analysis of variance is very similar to regression analysis, and we'll see that the only difference is that the descriptive variable, and in our case, the descriptive variable is ventilation, needs to be a factor. That is, should not be numeric variable. So the model object is calculated using LM function, the LM function that we're using in R, but we extract the output using ANOVA function in R. So let's do that. So we just do this. We say ANOVA. So let's start from here. LM. Then we have call it. That's our Y variable, or our variable of interest. Then we are grouping these according to ventilation. So that's the same model you are using. That's the same approach we're using for regression analysis. Actually, if I run this, I'll get a regression model, as you can see. But that's not what I want. I want to extract ANOVA. So you put ANOVA at the beginning there, then like that. I think there's a question somewhere. So this is the difference between what we did in linear regression and what we are doing now. Everything else is similar to what we did. But of course, we have said that we must set the grouping variable here into a factor, this one. Then we extract the output using this function. Now, when you run this, this is the kind of output that you are going to get. You get analysis of variance table. Of course, that tells you what exactly you have down there. Okay, the response variable is like your Y variable in regression analysis, it's called it. And of course, the other one is a grouping variable. The kind of notation that we get from R is slightly different from the explanations that we gave earlier on, because you can't see the sum of squares between, you can't see the sum of squares within. So the first line here, the one we are calling ventilation, this is the grouping variable, the grouping variables. So this is where you find so the first value here, you can see the degrees of freedom are 2, which is k minus 1. There are 3 groups minus 1. So k minus 1, 2. Then this sum of squares, this is the sum of squares. As you can see, this is sum square like that, in short. This is a sum of squares between groups. Okay, sum of squares between groups. Then this is the mean of the sum of squares between groups, MSSB. Okay, when you come to the second row, which is called the residuals, like the error term, these are the within. As you can see, the degrees of freedom, capital N minus K minus 1, which is 19. Okay, how many observations do we have, by the way? The dimension of red. So there were 22 observations, minus 3, minus 1. So 22 minus 3 minus 1. Oh, sorry, this is n minus k, sorry, n minus k. So it's 23 minus 22 minus 3 is 19. Then this is the sum of squares within. Sum of squares within. And then this is the mean sum of squares within. The mean sum of squares within. So this is the other variance. Okay. Then if you take this value, divide by this, you'll get this F statistic. This is the F statistic we're talking about. And this is what you want to check whether it is significant or not. The null hypothesis says that the ratio is 1. In other words, this mean sum of squares is equal to this mean sum of squares. So you test that hypothesis against the hypothesis that the ratio between this and this is greater than 1. Almost all the cases, this guy will always be bigger than the lower one. So you have this. You have this. Then this is your p-value. This is your p-value, which is significant at alpha is 5%. It is significant at alpha is 5%. Meaning that you are supposed to reject the null hypothesis that the group means are equal. That means that you are supposed to reject the null hypothesis that the 3 groups have equal means. So basically that is it. So in this case, we would reject the null hypothesis that the group means are equal. Of course, as you can see, the p-value is at the border point. That the border point is very close to 0.05. So you may want to explore using some other technique whether actually you are going to have the same conclusion. Like, for example, you can use the non-parametric approach and see if you're going to get some consistency. Okay, so basically that's how you perform analysis of variance, what you call the one-way analysis of variance using R. Okay, so I want us to answer the question that was posed by one of you by looking at this example. Unless there's a question there, let me know if there's a question there. So let's look at this data set known as Joule, J-U-U-L, from our library there. So then I'm calling the data here. Then I want to view the data. So when you click view the data, this is how the data looks like. So there are several variables and there are so many missing observations in this data. Okay, so we have age, we have menage, we have sex, there is IGF-1, there is tana, there is test volume, something like that. Okay, of course, I'll be interested in this particular column, which is and that's a numeric variable. Then I'll also be concerned with this column here, tana. If you look at tana here, it is taking the values. Of course, they are missing values. Then there is 1. There is all the way. The data set is a little bit large. Okay, but I can just say summary. Let me say summary. I want to call the summary of summary of this particular data set, but I want to pick which columns. I want to pick column 4 and 5 only. The code will work. Yeah. So I've extracted these 2 columns because those are the ones I'm interested in. So I don't need the others. Okay. So I want to illustrate the concept using these. So the first variable IGF1, if you want to understand the meaning of all these variables, you just come here and do this. You ask that. When you ask that, it will give you the descriptions here. It will give you the descriptions here. Okay. So this data frame has this number of rows and 6 columns. It contains a reference sample of the distribution of insulin-like growth factor, IGF-1. So that's this variable we're talking about, insulin growth factor, insulin growth-like factor, insulin-like growth factor, sorry. Then we have tana. So 1 observation per subject in various stages, with the bulk of the data collected in connection with school physical examinations. We have age, this is a numeric vector in years. Then MENAC, this is a numeric vector, has MENAC occurred, which is coded 1 for no and 2 for yes. Then sex is a numeric vector, taking 1 for boy and 2 for girl. Then IGF-1 is a numeric vector, insulin-like growth factor, microgram per liter. Then tana is a numeric vector. So this is very important, is a numeric vector. So this is not a factor at all, okay? With codes 1 to 5, stages of puberty, and some other thing here, then, and so on and so forth, okay? So these values here are numeric values. They may look like they are levels, like the ones we had in the case of ventilation 1, 2, and 3, but this is different. And of course, you can see there are many missing observations, which of course will be deleted when you are doing the analysis. Another way of doing that, if you want to confirm that the grouping variable is actually a factor, you can check the, yeah, so saying that if you want to confirm whether your grouping variable is actually a factor, you can use this function structure. Then I want the structure of what? Because I've not attached yet, I say this, picking that particular variable, tana. So what is the structure of that variable? As you can see, this is a structure. It's not a factor, it's an integer. It's an integer. Okay, of course, with missing values, then it's also taking values 1, 1, 2, 2, 3, 4, and 5, so on and so forth. So we need to convert this particular variable, that is tana, from a numeric variable to a factor. Okay, so we'll be doing that. We'll be doing that. And that answers the question that was posed by someone. How do you deal with a scenario when the grouping variable is actually not a factor? So that's the answer. You check, you confirm that it's not a factor, then I'll be showing you how to convert it. So back to our code, we have the data. Then it's always good you attach the data to make your work a little bit easier. Attach this one. Okay. Then I want to show a few of the observations. And I want to use the new function kable. Then I want to pick some rows. I want to pick some rows 40 to 46. I want to pick these particular rows. And so now I don't want to see the top 6 or the last 6. I also don't want to choose at random. I want to pick from the 40th to 46th individual. I want to see how the data looks like there, down there. So this is how the data looks like. Okay, from the 40th guy to the 46th individual, these are their ages. The other variables are here. They are missing values for this one. They are all boys. And these are the IGF-1 values. Then tana is 1, and then the other variable was the variable has missing values. Okay. Then of course we have done this. We have done the structure. Now we can check again the structure of tana. Now I don't need to put the dollar because I've attached the data, and we have seen that is an integer. Okay. Now, if you run an ANOVA using this variable tana, the way it is, you'll end up with the wrong results. You'll end up with the wrong results. It will try to perform a regression analysis, assuming that you are regressing, let's say, your y variable on this tana here. For example, if you do this, then you say lm of this is IGF1 by tana. If you do that, this is the wrong way of running the model. So let me put a hash. This is wrong. This is how you are not supposed to do it, because this guy here is not a factor. That's what is wrong about that. Okay, and it will be indicated here because you expected that tana will have 5 levels. So we expected that k will be 5 minus 1. So we expected a 4 here, but now it's just 1. So it's taking this as a variable, as a continuous, as a quantitative variable, which is not the case. Okay, and as you can see, even the degrees of freedom in the other variable here are also wrong. Okay, so to avoid that, we need to define tana as a factor. We need to define tana as a factor, and this is how we're going to do it. So define as a factor. So we can define a new variable here now, joule, dollar, tana. So we say I want to rename this. So this will be factor. So that's how you do it. And maybe before I type the code, you can say, I want you to see these. I want you to see this explanation here. That's the advantage of using RStudio. The function factor is used to encode a vector as a factor. The terms category and enumerator type are also used as factors. Okay, so we are trying to convert this variable into a categorical variable. Okay, if argument ordered is true, then the factor levels are assumed to be ordered. Okay, for compatibility with S, there is also a function ordered. So S is an order language. Actually, is the language that came before the language that we use in R. Okay, so but those are stories for another day. So we say factor, then we write the name of the variable that we want to transform. So this is joule, then dollar, tana. Then what should be the names of the levels? So we say that labels. So labels. So the labels will give me the levels, or the group names. So I want to call them, and because these are non-quantitative, I'll be putting them in quotes. Then we have 2. There are 5 from what we observed earlier on. 3. Then we have 4. What happened here? So we have 4. And then we have 5. So those are the levels, and those are the labels. So the group labels will be 1, 2, 3, 4, 5, using the Roman letters, not numeric values. Okay. So when we run this, that is okay. Put this down here. Then I want to detach. I already had attached this data, so I want to detach it so that we forget the older variable tana. So detach joule. I want to detach that. And now I want to attach it so that it picks the new description of or the new structure of my new variable. So I'll also attach rule like that. Okay, so if you do that now and you check the structure of Joule Tana, if you do that, if you check the structure, you will notice that our new variable Tana is now a factor with 5 levels. And the levels are level 1 in Roman 1, Roman 2, all the way to level 5. And of course, they are missing values, which will be deleted when you are doing the analysis, of course. Okay. So after that, now we can, rerun. We can rerun the model again. So ANOVA, where this is, this is LM of IG F1 described by Tana. Now that we have confirmed that Tana is a factor, so we can run our ANOVA like that. And this is these results are now what we expected. This is our ANOVA table. The response variable is IGF1. Tana is a grouping variable, and we know it has 5 groups, so the degrees of freedom is 5 minus 1. The mean sum of squares between groups, the sum of squares between groups, the mean sum of squares between groups is here. And then the residuals here correspond with the within group kind of variation. So the degrees of freedom are here. Okay, so of course so many variables have been deleted, the one with NS. Then the sum of squares within groups and the mean sum of squares within groups. And when you take this, you divide by that, you will get the F statistic here. It's obviously significant. Okay, it's obviously significant, meaning that the group means are not equal, Okay, so this kind of test is based on the assumption that the variances, the group variances are equal. This kind of test is based on the assumption that the group variances are equal. So if that is relaxed, just like we did in the case of testing hypothesis for 2 samples, if we relax that, we need to use another kind of test. Which is equivalent to the Welch test that we used in 1 sample and in 2 sample tests, sorry. Okay, so in this case, if you relax the assumption of equal variances, so let's say that, so relaxing the assumption of equal variances. So in this case, we use a slightly different code, but the other story is almost the same. So we use what you call one-way test, just like one-way analysis of variance test. So one way, but now you just say for let. I'm going back to my original example, then ventilation. This is our first example, so we're going back to that. So here we don't put the LM. We don't put the LM. If you allow variances to be different, then this is the kind of function that you use, one-way dot test. Then you have the response variable and the grouping variable. So when you run this code, this is the table that you'll get. Analysis of variance table. Sorry, we're here, down here. We have here one-way analysis of means. Okay, and we are in brackets, not assuming equal variances. So in the first kind of analysis of variance, the assumption was that the groups have equal variances. So when you relax that assumption, this is what you do and this is what you get. So the data is folate and ventilation. Then the F statistic is this. And as expected, when you relax this assumption, the degrees of freedom are usually in decimal values or decimal format. So the numerator degrees of freedom is 2.0 and the denominator degrees of freedom is 11.065. and the p-value is this one, which is not significant. So meaning that we are not able to reject, or we fail to reject the null hypothesis. So we notice that the p-value has increased to an insignificant value, and presumably this is because of the fact that the group that seems to differ from the other two has also the largest variance. So if that happens, that may explain why the p-value is now larger than the level of significance. Okay. So, but you may want to check whether you need to relax this assumption. You may want to confirm whether you need to assume that the variances are not equal. Okay. So if you want to check whether the variances are actually equal, if you want to be sure before either using one-way.test or using the ANOVA function, you may want to use what you call the Bartlett test. Or this is called the Bartlett. Bartlett's test, to test for equality of variances. Okay, so and here you just say Bartlett dot test, then you say Follett, you group by ventilation. You want to see if the variance of Follett for the three groups is actually equal. So when you run this, you notice that you have this is the output, Bartlett's test for homogeneity of variances, that is equality of variances. This is the data. Then the Bartlett's k-squared is 2.09 something, degrees of freedom is that, and the p-value is 0.3508. Okay, so that means that you fail to reject the assumption that the variances are equal. So there's nothing to suggest that the group variances are different. From this kind of test, there's nothing to suggest that the group variances are test. So that means that this kind of test here is not necessary for this kind of data. So the first test is actually the appropriate test. The first test that we did is the appropriate kind of test. Okay. Any question? So what we've been looking at is the parametric procedure of one-way analysis of variance. So now I want us to look at the non-parametric counterpart, and this is called the Kruskal-Wallis test. Okay. So this is how we implement the Kruskal-Wallis test in R. So we use the function Kruskal.test. Then we're checking for the means of Follett being grouped by ventilation. Then you run the code. Okay. This being an unparametric procedure, just like the Welch test, we are replacing the data using ranks. So that's why you can say Kruskal-Wallis rank sum test. Okay. The data is as explained there. Then Kruskal-Wallis chi-squared, the test statistic or the calculated statistic is 4.1852 with 2 degrees of freedom. And the p-value is 0.1234. Okay, which is clearly not significant. So that means that we failed to reject the null hypothesis. We failed. So we say that it seems that there is no significant difference using this test. So the difference is not significant. The difference of means is not significant. So we can assume that the group means are equal, in other words. So I'm sure you can see that this kind of test is contradicting what we saw earlier on. But it's good to remember that the p-value that we got using the parametric method was 0.04359. 0.04359, which is at the border point. So when you see that this is not significant, you should not be very much surprised, because even the other one was just almost at the border point. Okay. So you notice that the Kruskal-Wallis test is also less efficient. It is less efficient than the parametric counterpart if the assumption, especially the assumption of equality of variance, is true. So if the assumption of variance is true, then the Kruskal-Wallis test is less efficient. So we prefer to use the parametric approach, not this one. And we saw that in our example, the assumption of equality of variances was valid. So we prefer the results that are given up there than the ones that we have down here. Okay, so basically that is it. That's how you perform one-way analysis of variance using the parametric and non-parametric approach. Any question? So this is your reading exercise. You read about two-way analysis of variance. This is when you have two grouping variables, like in the case of ventilation. Ventilation was our only grouping variable. So if you increase, if you put another grouping variable, like maybe the best example is the second example that we looked at. If you have another grouping variable, then we'll talk about a two-way analysis of variance. Okay, so I want you to check the parametric way of performing analysis of variance, two-way analysis of variance using R, and also the non-parametric test, which is called the Friedman test using R. And I've asked you to illustrate that using this particular data set, heart.rate, in the library that we've been using. And I also want you to extract the ANOVA table in regression analysis. And I'm referring you to our previous examples where we were using shot.velocity and blood.glucose. We fitted the model up there and we were calling the model myFit1. And I've showed you that this is the model that we fitted earlier on. myFit1 is LM of that. So basically what we are doing here, we're just putting ANOVA here. So we're just removing this part here. And then we say ANOVA. Then we enclose these. So it's similar to what we have just been doing in this class. So you extract that, and I've done that for you. So this is the ANOVA table. The response variable in that regression model is shot.velocity. And unlike in the case where we have groups, so here blood.glucose is not a grouping variable. Okay, it's not a grouping variable. So so this is equivalent to the between group variation. It is equivalent to that. So in regression analysis, in some software will report this one as the regression. They'll call this part the regression or the explained part of the model, and this other part, the residuals, is the unexplained part of the model. So this one corresponds to the explained sum of squares, and this one corresponds to the unexplained sum of squares or the residual sum of squares. So sometimes this is called the residual sum of squares, and this is called the regression sum of squares or explained sum of squares. Then we have the corresponding means by dividing this guy here by the corresponding degrees of freedom here. So you also take this divided by the corresponding degrees of freedom. Then you get the F statistic by dividing the two means or the two variances. You get this. You get this, and the p-value is here. And I'm posing the question, are there any similarities in this and the previous output? When you look at this output, and the output that I showed you up there, this output, are there any similarities? Maybe the first thing you'll notice that the p-value here, which corresponds to the slope coefficient, is the same. This p-value is the same one we have down there. Okay, this t statistic here, or the t-value, if you square it, you'll end up with this f. Okay, so basically this table is doing the same job as we did up there. The same job as we did up there. Okay, so check those ones after class. Then we can be sharing notes after this. So with that, that marks the end of today's class. I don't know whether there are any more questions before we call off the class. If there are no questions, we meet next week. Thank you.